So I hope that you understand. There was a typo in question 3. So FS is not correct. It is just DL. So I think that is the answer for that. I just checked it during the break time. So anyway, so far we were able to show that our verifier, or prover, which is authority, is able to prove that he used the correct information for the computation. But in the last page, we discussed about this zero knowledge proof of system, that we showed that we can prove that our simulator can run in an expected polynomial time. But what we can do about it is that, what if we swap that verifier with the honest verifier, and in case that we assume that our verifier, which are the voters here, the users in the system, they want to verify the votes, are basically honest. And if that is the case, then the idea would be like eventually we can replace it with a hash function. So what we are discussing here, we said that we send some value. So this is a prover, this is a verifier, and then he sends the challenge, and then we respond. So the idea is that, what if we remove this line? So we assume that the verifier is honest, so we just replace it with some hash function. So if we do so, so let me see what is the probability for those transcripts. So for the probability for those transcripts, that when the prover is communicating with the actual verifier, that here it doesn't have a star, which means that it is honest, on this knowledge X, is that we have A1, A2, and then B, and then C, right? These was our transaction values. So we know that we choose a R, and based on that R, we compute A1 and A2. So if I go back, so you see that I choose R, and based on that, I compute A1 and A2. So the randomness of A1 and A2 is dependent on R. Okay, so that is given. Okay, so that means that if I want to compute this probability, there is 1 Q chance, 1 out of Q chance to choose that. And then B is pretty much computed, and C is also a randomness. So for C, I have 1 over Q chances, right? So every C has a probability of 1 over Q. Suppose it is being chosen randomly. So the probability of this values, any of this A1, A2, B, and C integer to become a valid, set of transcript is only 1 over Q squared. So now if we know that we are replacing that or verifier with the honest verifier, so therefore we won't interact with the verifier. So that means that our simulator would change. So in the simulator, we choose a B, randomly choose a B, and then randomly choose a C, and then we compute A1 and A2 in the following way, and then we can pretty much return. And this is going to be a valid point, because well, we know that the correctness was verified. So there are two things we need to check, and that is like the if these two the output of this two word simulator versus prover verifier are identical, and that is indeed identical, because if you look at over here, we choose a B and C, so 1 over Q for B, 1 over Q for C, and then A1 and A2 are fixed, right? So the probability of this integer to form a valid transcript is only 1 over Q squared. And then if now you look into the runtime, because we assume that there is a honest verifier, we get rid of that line, the if line, that if the challenge that we choose is, we guess, is correctly. So if I go back, so the challenge was in this line number 3, that we have to make sure that we guess a correct challenge. But now that we have swap the verifier with the hash function, or we assume is honest, we won't actually execute the verifier. So, but you see that if that is the case, and we always draw a random value for challenge, then our expected runtime is also a polynomial time, because all these steps are polynomial time, and therefore now we have an honest now we have a zero knowledge proof for this. So this is very interesting so far. So we are able to swap them with with some few changes. We can even prove that we have a zero knowledge proof. So again, so we are replacing the verifier, the challenge, with the hash function. So instead of generating a random challenge, we are going to use this hash function that would compute this based upon this G1, G2, Y1, Y2, A1, and A2. And then the proof of the work is just going to be a CNB. So if you have an authority J, then he wants to prove that his work is correct. So he has to prove that he used the same thing, the same H of S for these two computation, G of Sj, and then Wj, which is equal to C1 tilde of Sj. So this one was done with the Tali, because in the setup of the system, the Tali has set up this public parameters for it, but he shared this secret Sj to this authority J. And if this authority J is honest, he should use the same Sj for computing Wj. And then we are able to show that we can prove that by just providing this two integers C and B. And therefore, we are able to verify the correctness of the computation provided by authority AJ. So let me put it in a bit more perspective. So in the public parameters, we have H1, H2, all the way to Hn, where Hi equals to G to the power Si. So these are given. So we have A1, he computes W1, we have A2, he computes W2, and then all the way to we have AN that computes WN, right? And then now they can provide a proof of work C1 and B1 for their computation of W. So oops, C2 and B2 and Cn and Bn. And then we can verify the AG now. For example, the authority J. We know that by using Wj and Hj, because they should use the same exponent for them, the same the same Sj for that computation. So then we can use the Cj and basically Bj to verify that computation, that they are indeed this authority J indeed uses correct share Sj for doing this computation of Wj. And now we know that out of this scheme, A star J, that an dishonest authority, cheating probability is only 1 over Q, right? So there is a very, very, very tiny chance that this guy could use a wrong Sj, but he can convince us that he used this right Sj, and that probability is 1 over Q. And we know that our Q is quite large, so this probability is almost negligible. So it looks like that the way that we are verifying this authorities is a right way. All right, so this is a part of the work that we should have done to verify everything is correct, the computation, and therefore now that we know that the computation is correct, when we verify them, we can utilize them to compute the final vote. So the only piece of other work that we have to do is the voter proof. So we said that the votes, we have to also make sure that they are in a correct format, and also we need the voters to prove that actually they are writing in a correct format. So if you imagine every vote CI, we said that we have CI1 and then we have CIN2. We have two pieces, which is equal to G to the alpha I, and then G to the VI, H to the alpha I. And then we said that the VI has to be from the set, either -1 or +1. And therefore, we do not want this VI to be from this, let's say, VI star set from +10 and -10, right? So we want everybody to vote either yes or no, not 10 yes, not 10 no, right? So this is what we are going to spend some time now to see how we can do that. So we said that so the challenge over here is that the VI is either +1 or +2, so +1 or -1. So the prover has to prove one of these two things. If he has proven for no, then he can prove the he can use the same proof of equality for using the same exponent for two different bases. And then but we have to multiply to G +1, and then otherwise we multiply to G -1 so that we make the results equal. So let me expand on this to see what do we mean. So if we do proof of work log equality, so from the first one we get G. CI1 is G to the power alpha I, and then we get our H, and then we get G +1, that we basically add this one. We don't have this G in the first place. We add a G +1 so that we make, no matter if you yes or no, the resulting would be the same. And then to the power G -1, if this vote was no, H alpha I. So if the vote was a no, then we add G +1 so that we make this result the same. So therefore, we are going to do the log of equality for G and then G to the power alpha I, and then H, and then H to the power alpha I, right? So we see that we have two different bases, G and H, and then we raise them to the same power. So therefore, alpha I equals to log of G to the alpha I on basis G, and this is equals to log of H to the power alpha I on basis H, right? So it looks like we can use the same trick to do the computation. So again, I'm going to change the variables to be generic. G1 is G, Y1 is G to the power alpha I, G2 is H, and Y2 equals to alpha to the H to the power alpha I, and X is equals to alpha I, right? So this is how we are going to prepare ourselves for this proof. So we are going to prove that given this values, prover knows one of these logs, but not both of them. The idea is that, as we said in the previous page, we have to prove either one of them, either this one or the other one. But the problem is that if we just prove that our vote was indeed yes, that means that, well, we are leaking our vote, that we are telling the board that, you know, my vote is a yes, and therefore I provide the proof for a yes. Or otherwise, if this is a proof for proof of vote for no, and if I indeed prove it only for one of them, which is no, then again the whole world would know that what I vote for. So the idea is that we would prove both of them, that I prove for both yes and no, but only one of them is real, which is my vote, and the other one is just a simulation, so that the whole world would, when they would confirm that both of those, either I vote for yes or for no, both of them are correct, proof of work, but actually I vote for one of them. But because I provide the proof of work for both of them, then I don't leak what my vote was. So I think we would go through some examples over here to make this a bit more clear. So the case number one is that, if I'm a prover, okay, let me actually make a new page over here. I think this is going to be a bit lengthy. All right, so the public parameter is G1, Y1, G2, and Y2, and then Y1 is G1 to X1, and Y2 is G2 to X2. So we are going to show that we just know we can prove one of them, but not both of them. So the first case we are going to prove is that prover knows X1. So we want to show that the prover knows X1. So this means that we have a prover that knows some knowledge X1. And then he's going to randomly select R1 B2 and some C2, some challenge. And then he would send this information to the verifier saying that, hey, this A1 equals to G1 to the R1, and then A2 equals to G2 to the B2 and Y2 to the C2. Okay. And then the verifier would send a challenge to this guy, to the prover, and then so the prover would do this one. He would split C into C1 and C2 by defining C1 equals to C minus C2. So over here, he knows the X1, so he can prove this proof of equality, but he's simulating the second one. So he already guessed the piece of challenge for the second one. So that's what we are doing. And then when we receive a challenge, he splits the challenge by C1 equals to C minus C2. So this is what he gets and he's simulating. And then the leftovers of the challenge he's using for actual proof of work. And then he would return this value to the verifier by saying B1 equals to R1 minus C1 X1, and then B2, and then C1 and C2, right? So let me go through this one, and then we will come back and discuss it, what is happening here. So now the verifier needs to check. So the first thing that he check if C1 plus C2 equals to C. Number two, he check if A1 equals to G1 to the B1 and Y1 to the C1. And three, if A2 equals to G2 to the B2 and then Y2 to the C2. Okay. For example, let's discuss this case. So we know that G1 to the B1, which is going to be J1 R1 minus C1 X1 times G C1 X1 is going to be indeed G1 R1, right? So the computation is correct. So let's just see what is happening here. We are using the same scheme as before, but we are proving two things, two different log of x's. But the point is we know one of them, but we don't know the other one. So the idea is that we know this vote, that we casted this vote, so we are able to prove it. But the other votes that if I were to vote no, for example, I didn't vote for it. But so the point is like, I know that I didn't vote for it, but I can just simulate this one so that, you know, the transcript for this proof between this prover and verifier looks correct, so that the verifier at the end can verify both sides that, okay, I voted for both yes and no. Both of them are correct, but actually I voted only for one of them because I already know this X1. So I can craft my proof to be to be correct for one of them, the knowledge that I have, and then the other one I just simulated so that the verifier cannot tell which, you know, discrete logarithm I knew. So either I knew X1 or I know X2. So in the case that prover only knows X1, then in this case, we are able to prove for one side of the formula, but you see that the other side, so if I drew a line, so we are proving over here, and then we are simulating over here, right? So we are in two words. So at the same time, we are proving, and at the same time, we are simulating. One of them we are actually proving, and then we are using our knowledge X1 that we know. So you see that I'm plugging in X1, and I'm really showing that, you know I do have this knowledge and of X1, and because of that, I'm doing the computation. But for the other piece, I don't know the X2, so I'm just simulating it. So the beautiful design from this, slightly change over here is that when we guess the C2, the challenge that we are receiving for the other part, but when we get the C, we would split it and say that C1 equals to C minus C2. So we choose some part of the C for, we guessed it for the simulation, and then we use the other part for the actual proof. And since we have X1, so we have no problem for computing V1, and for B2, because we already guessed, and we don't have to do the computation, we would just return it. In return, we crafted A2 to be somehow that the recipient would accept it. So it turns out that we can do the same thing, the same thing for the other way around. So what if the prover knows X2, which is log of Y2 on basis G2. So again, we said that we have this prover with knowledge of X2, and then he selects B1, C1, and then R2, and then he would send, we are simulating the first half now, which A1 equals to G1, B1, Y1, C1, and then A2 equals to just G2 to the R2. And then we receive this challenge C, and then we would split again to C into C2 equals to C minus C1 now. And then we are able to do this computation by saying B1 and then B2. B1 is we already selected, we just send it, and then B2 equals to, we do have to compute this one, R2 minus C2 X2, and then we also return C1 and C2. So again, you would check these things, 1, C equals to C1 plus C2, 2, A1 equals to G1, B1, Y1, C1, and 3, A2 equals to J2, B2, Y2, C2. So if this is the case, then what we are seeing here is that A1, C1, and B1 is a simulated transcript. And then A2, C2 and B2 are real transcripts. Right? For G2 and Y2. So this way we are proving that we have done the correct work, our vote is correct. And at the same time, we are not leaking what we have voted for, right? So we are proving that, either if I want to vote for yes and no, according to this transcript, they are both correct. But we know that out of this construction, we are only able to prove for one of them, and we are not able to prove for the other one. And that probability for proving for both sides is just very low, so that we don't have to worry about it. So this is how we have our prover. We discussed how our authority J can prove their computation is correct. They use the correct piece of secret that they have to do the computation. We also prove that our voters, they voted correctly. That means that they voted from either yes or no. And, if they try to vote for something other than that, we can catch them in this proof. And therefore, we can also verify votes for every person. So the last piece that we need to discuss is this election without the trusted center, that we call it T. In the beginning, we said that we need this trusted center. If I go back, right over here. So we said that we need a trusted T to set up our system, to choose the prime, to form this polynomial, compute the share for everybody. But we also discussed that it would be the best if we can get rid of this setup, so that we don't need to trust one person to set up the system. This is the page that we want to discuss about it. This is how we are going to do this computation. So we assume that there is a group P, and where it look like to be in the format of KQ plus 1, and the generators are given. So these are the public information, okay? Publicly given. There are a lot of groups indeed that are available and publicly, so we don't have to really worry about setting up this. We can just utilize those groups. So the idea is that every authority I would basically form its own polynomial called fi of x, and then we'd also would choose his piece of secret xi, and so that the fi of 0 is that secret. And then he also would publish his hi, and then so let me actually go ahead and write this down in our own language. I think I leave this one, the textbook format, for you to read, but this is going to be the way that I would like to explain it. So the overall idea is that instead of the trusted T to set up f of x, where this is at minus 1, xt minus 1, plus at minus 2, at minus 2. Right? Instead of we have our trusted T, the trusted T's to set up this formula, we would break this formula into this, and we break f of x to be like this format: f1 of x plus f2 of x all the way to fn of x, right? So we break this polynomial into n different polynomials. So this is how we want to see this polynomial f of x. So now each AI, authority AI, you would select its polynomial and secret SI by this way. So every authority would basically choose a different polynomial. So it's going to be AT-1 for authority I, x to the power t-1 plus AT-2 of this authority I, xt-2 all the way to AI of x1 plus si, right? And also he computes and publishes hi equals to g to the power si, right? Of course, mod p, and we'll publish this one. So now that AI has, computed this thing, so now you can imagine that when everybody, compute this polynomial, so then they can publish their polynomials, and at the end, they all can add them up together to compute this overall f of x, which is just addition of them. But the point is, before they can do so, they also, it's one way to see this one, but the other way to basically every other user to get their different shares from these polynomials and therefore compute their own polynomial, we have to do a little bit of more trick over here. Okay. So in order to compute the secret of every polynomial, so now this guy AI has to compute the S1 and 1, Si and 1, which is the Fi and 1. So for every other user, they have to compute the piece of share based on this polynomial made. So the piece of share from user I for the user 2 is Fi of 2 and so on and so forth. So they compute all this thing Xi for user n is equal to be Fi of n. And then they would send these pieces through a secure channel to other authorities, A1, A2, all the way to AN, right? So right now that, everybody has set up their polynomial and, all those stuff. So, this SI is actually, it is the secret key piece that this user I has chosen. So when you add up these polynomials, these values will change. So suppose now that everybody has done that computation, that suppose AI receives S1 for user I, which is going to be F1 of I. S2 of for user I is going to be F2 of I. So every other user, when they set up this polynomial, they are going to compute the point for this user I, the authority I, and they are doing so by just computing the I on their own polynomial. So S3 for user I is going to be F3 for I, all the way to Sn of I, which is f of n of I. And once we get this one, then we can compute Si to be f1 of 1, I, plus f2 of I, plus f3 of I, all the way to n of I, which is going to be equal to the f of I, right? So the S of I, the secret key that for this user SI, we can just plug it in. It has to come through here. So this is how it works. So eventually we want to combine all these FI, functions together to form the actual function f of x. But if you notice, every user, every authority has its own function. He doesn't know the other ones, and we don't want to share the actual functions to for everyone to compute this f of x. So the only thing we want to share is that every authority would compute the point for every other user and share it to them through a secure channel. So suppose that AI, user authority AI, receive its piece of share from function f1, f2, f3, fn from the other users that they have, formed their private polynomial. So and when we add them all together, we would compute the SI, which would be the actual share of user AI, and then we can go ahead and compute, the public parameter HI equals to G to the SI. So this is pretty much the idea of how we do it. So we don't have to share the polynomial. Everybody will set up their own polynomial, but in a sense, the way that we are doing the thing and combining this, the values, the points, is just like we combine these functions. Somebody has shared the functions and we add them up together, and we are basically doing the point computation based on that overall function f of x. But we don't have to do that. The other way around is that every individual can use their f1, f2, f3 function to compute their share for point I, and then we add them up together to compute the f of y, right? So we kind of break down the function. We don't have to put them together. We can also use the streak to do it. And the advantage is that we don't have to share the polynomials between every user. So this would be an idea of, for everyone to compute their, we don't need to have that trusted third party to set up the system for us. So the authorities can collaboratively do this computation. You can also imagine that we can add some, with the knowledge that we have learned, proof of equality and those stuff. We could also, add some proof of work for every of these individual ones, so that we make sure that the values that are being shared or computed from different authorities are correct, right? So we can also provide the proof of work for every piece that we receive, so that our algorithm is concrete. So if you go back to the requirements that we had in the beginning of the setup, so you see that now that everyone votes, we don't use a signature, but we actually use a better idea. We use a proof of work that indeed, this vote is correct. And nobody can just change the votes because, we have a proof of work and that wouldn't match. So the votes are secret. The commitment scheme that we use to cast the votes is secret, so that is fine. We authenticate the votes through that, log of equality, so that they are authentic and they are correct. So make sure that every vote is counted. We achieve this by making sure that when we multiply them together, so the CITs and those stuff that we get, if they're not correct, so we can catch those tallies or authorities that they don't multiply them correctly, so they are unable to provide us a proof of work. So we would catch them there, and nothing can be tempered. So because every piece that we have put together, we have a proper proof of work, and the elements that we use to achieve the security of the system is also, we have done a pretty good work, and we make sure that they are basically sound and correct. So all together, if we put them together, I think we have a complete system now. at least you have experience how to design one of the systems. And so we see that, we have put multiple things together to ensure the security of the system. So I hope that this is a good example for you to see how we construct a protocol like this. So, this could be a different protocol for you when in the real world you want to solve problems. It doesn't have to be counting only votes. It could be a different computation, but at least now you have a generic framework in your head that, if there are servers and they want to, add or do their computation and they want to use some public, servers such as authorities, you want to utilize them to do the computation. At least now you have a system that you can achieve it. You just need to slightly change the things so that you can make sure that you can carry out a different computation that you want to do. Of course, here our focus was only to do a voting system. All right, I think the rest of the lecture is just talking about blind signatures, and we are just going to skip them for this year. We don't have the time to go through them. I think you already have some idea of what are the blind signatures are, but nothing so much important that we would have to spend some time there. So we unfortunately missed them. But I am so glad that we were able to finish this election system. So this is something that we always make sure that we can finish every year. So yeah, I think this is officially the materials that we wanted to cover. Do we have any questions? All right. If you don't have a question, thank you so much, guys, for being with us, taking this course with us. It was quite much of fun to be with you and share these pieces together. And at the end, we made it to here that we could design a secure protocol together. So be prepared for your final exam that would be on the next week. And don't forget to submit your homework online on time. And then for, I think, next semester, we are offering the course called Network Security. For those that they haven't taken this course, we would want to welcome you to join us for the course for the next semester as well. I think it's going to be the same format. It's going to be online. We have quite a large number of students attending the course. So of course we wouldn't be able to adjust, to get a place at the university to do it. And actually, I think it is such a privilege to have the courses online, so everybody can just sit down home and enjoy the lectures. Will the Ch5 note uploaded to the, yes, so the chapter 5 right now, after the class, I'm going to upload this noted slides to the EE class platform so that you can prepare for your final exam. All right, if there are no more questions, it was a very fun semester, guys, together. I hope I could see some of you for the next semester, and thank you for taking this course with us. Have fun.